In our modern world, we are quite rightly dazzled by the grand scientific discoveries that pepper our news feeds. We marvel at breathtaking images of distant galaxies, at the intricate climate models predicting our planet, and at the mind-bending quantum theories. These are the front-page stories, the stuff of Nobel Prizes and public fascination. Yet behind this grand theatre of human achievement, there exists a hidden world of tools and their makers, a world without which most of this progress would simply grind to a halt. In this realm of quiet foundational brilliance, few figures loom as large as James Demmel. He is, in a very real sense, one of the principal architects of the computational scaffolding upon which modern science is built. To put it simply, James Demmel is the man who made the numbers work. He didn't just write code, he forged the very language that allows supercomputers to speak sense. Imagine trying to build a skyscraper with tools that might buckle or break at any moment. That was the state of scientific computing before Demmel and his collaborators stepped in. They crafted reliable, robust, and astonishingly efficient software libraries that scientists now seemingly take for granted, forgetting the foundations at which it was built. Think of it like this. When you watch a magnificent orchestra perform a symphony, you seldom spare a thought for the luthiers who crafted the instruments with such precision that they can produce those perfect notes, or the acousticians who designed the hall to carry the sound flawlessly. James Demmel is that master luthier and chief acoustician for the grand orchestra of scientific computation. The seeds of this computational revolution were sown early in the fertile mind of a young man fascinated by the elegant certainty of mathematics, logic, structure, and problem-solving. It was a passion that found its first major crucible at Caltech, with sun-drenched courtyards and an intense intellectual atmosphere. He graduated in 1975 with a Bachelor of Science in Mathematics. But pure mathematics, for all its beauty, was only the beginning of the story. The 1970s was a period of explosive growth in computing, a time when the digital frontier was expanding at a dizzying pace. Demmel saw the immense potential in bridging the pristine world of mathematical theory with the messy, practical challenges of computation. This ambition led him to the University of California, Berkeley, where he would pursue his PhD, but not continuing in pure mathematics, instead switching over to computer science. At Berkeley, Demmel found himself under the mentorship of the legendary William Kahan, the primary architect of the Institute of Electrical and Electronics Engineers' 754 technical standard for floating-point arithmetic, the very grammar of how computers handle non-integer numbers. Kahan's rigorous, almost fanatical pursuit of numerical accuracy instilled in Demmel a deep appreciation for the subtleties and pitfalls of digital calculation. It was not enough for a computer to be fast. It had to be right. In 1983, Demmel completed his PhD, his doctoral thesis laying the groundwork for what would become his life's work, creating algorithms that were fast, efficient, numerically stable and reliable. It is a rare and wonderful thing when a professional partnership blossoms into a lifelong personal one, creating a synergy that elevates the work of both individuals to extraordinary new heights. Such is the story of James Demmel and Catherine Jellick. Their meeting at MIT, and later collaboration at UC Berkeley, marked the beginning of one of the most fruitful and influential partnerships in the history of computer science. Jellick was a formidable computer scientist and leading expert in parallel computing. She shared Demmel's vision for making high-performance computing more accessible, more powerful, and more productive for the scientific community. Their intellectual interests aligned perfectly, creating a dynamic duo poised to reshape the field. Jellick's expertise was in parallel systems, the art and science of making many processors work together on a single massive problem, while Demmel focused on numerical algorithms, the core mathematical recipes that run on these powerful machines. It was a match made in computational heaven. He designed the what, intricate mathematical operation. She mastered the how, orchestrating those operations across thousands of processors. Together they could tackle the entire pipeline from abstract mathematical theory to practical implementation on the world's fastest computers. Their work was not just complementary, it was symbiotic. Their professional collaboration was mirrored by a deep personal connection, and they were married, cementing a partnership beyond the laboratory. This union created an environment of constant intellectual exchange. Shared passion and mutual respect fueled their innovation, allowing a unified perspective greater than the sum of its parts. Together, they are a power couple of science and technology, leading the charge of computational innovation. If scientific computing were a language, James Demmel would be one of its most important lexicographers. He didn't just use the language. He created some of its most essential and widely used words. His most famous contributions are a trio of software libraries, LAPACK, Scalable LAPACK, and SuperLU. Their impact has been monumental. These are not applications you would ever download onto your phone, but they power the software that potentially designed that phone. They help forecast the weather today and modeled airflow over plane wings. They are the fundamental building blocks for solving problems in linear algebra, the mathematical workhorse of science and engineering. First came LAPACK, standing for Linear Algebra Package. Developed in the late 1980s as a successor to older, less efficient libraries, LAPACK provides standardized, highly optimized, rigorously tested routines for the most common linear algebra problems. Think of it as a master toolkit for mathematicians and scientists. Instead of every researcher writing their own buggy, slow code to solve linear systems or find eigenvalues, they could call a LAPACK routine. This guaranteed answers that were fast, thanks to clever use of computer architecture, and accurate and reliable, thanks to deep numerical theory. As computers grew from single-processor machines into massive parallel supercomputers, a new challenge arose. This led to ScaLAPACK, the Scalable Linear Algebra Package. Finally, for sparse matrices, mostly zeros common in structural mechanics and electrical circuits, Demmel led the development of SuperLU, a software library for supernodal lower-upper decomposition factorization, designed for high-performance solution of linear systems of equations. SuperLU is hyper-optimized for sparse systems, which can be incredibly gigantic, with systems only getting larger as artificial intelligence and large data continued to exponentially improve and grow. While creating powerful software is an incredible feat of engineering, James Demmel's most profound contributions arguably lie in the theoretical realm that underpins it all. His lifelong quest has been to solve a fundamental dilemma of computing. How can we trust the answers our computers give us? Computers, after all, do not work with the infinite precision of pure mathematics. They use a finite representation of numbers known as floating-point arithmetic, which inevitably introduces tiny rounding errors at every step of a calculation. For a simple sum, this is trivial. But in a scientific simulation involving billions of operations, these tiny errors can accumulate and cascade, potentially rendering the final result complete nonsense. Demmel became a world leader in the field of numerical stability, which is the study of how these errors propagate through algorithms. He didn't just want algorithms that were fast. He wanted algorithms that were backward stable. This is a beautifully elegant concept. An algorithm is backward stable if the answer it produces, despite small rounding errors, is the exact correct answer to a slightly modified version of the original problem. In other words, the algorithm is so robust that any inaccuracies can be explained by a tiny, acceptable uncertainty in the input data itself. This provides a powerful guarantee of reliability, assuring scientists that their computed results are meaningful and physically plausible. One of his most significant theoretical breakthroughs was in developing what are known as communication-avoiding algorithms. In modern supercomputers, the bottleneck is often not the speed of calculation, but the time and energy spent moving data between processors or between different levels of memory. It's kind of like having a team of brilliant mathematicians who have to spend most of their day walking back and forth to a library at the other end of campus. Demmel pioneered a revolutionary approach to redesigning algorithms from the ground up to minimize this communication. This research was not merely an incremental improvement, it was an absolute paradigm shift. James Demmel's influence extends far beyond his own research and coding. He has been a consummate academic leader, shaping the direction of computer science and computational science at some of the world's most prestigious institutions. His career path after his doctorate took him first to the Courant Institute of Mathematical Sciences at New York University, another powerhouse of applied mathematics, where he spent 7 years researching, from 1983 to 1990. At Courant, he further refined his expertise in numerical analysis, beginning to establish himself as a rising star in the field, contributing to the vibrant intellectual life of the institution and laying more of the foundational work that would lead to his later triumphs. In 1990, he returned to his alma mater, UC Berkeley, as a faculty member, a move that would solidify his position at the heart of the computer science world. At Berkeley, he has held numerous leadership roles, including serving as chair of the Computer Science Division and later as chair of the Department of Electrical Engineering and Computer Sciences. He was not just a researcher, but a builder of institution. He helped guide the curriculum, recruit top-tier faculty, and foster an environment of interdisciplinary collaboration that has kept Berkeley at the forefront of technological innovation for decades. Demmel has been a pivotal figure in connecting academia with the United States National Laboratory System, the epicenters of large-scale scientific computing. This role as a bridge builder has been one of Demmel's most significant, albeit less visible, contributions. In these roles, he helped to set the national agenda for high-performance computing, continually leading the charge in the computational revolution. A career as foundational and impactful as James Demmel's does not go unnoticed by one's peers. While he has never been one to seek the limelight, the scientific community has repeatedly recognized his contributions with its highest honors. His trophy case, so to speak, is filled with a constellation of awards, a who's who of computer science and applied mathematics. Each award tells a piece of the story, highlighting a different facet of his monumental career. Theoretical insights, practical software engineering, and leadership in the field. These are not merely trophies, but affirmations from the world's experts of the profound and lasting nature of his work. Among his earliest major recognitions were the Presidential Young Investigator Award from the National Science Foundation and the J.H. Wilkinson Prize for Numerical Software, now administered by the Society for Industrial and Applied Mathematics, highlighting practical implementation of brilliant numerical ideas. In 1999, he was elected to the National Academy of Engineering, an honor for outstanding contributions to engineering research, practice, or education. This recognized his work not just as abstract mathematics, but as engineering, reliable, high-performance software with real-world impact. The accolades continued to pour in. In 2010, he received the IEEE Computer Society's Sidney Fernbach Award, cited for his leadership in creating LAPACK and ScaLAPACK. In 2011, he was elected to the National Academy of Sciences, a rare honor for a computer scientist. He is also a fellow of the Association for Computing Machinery, the Institute of Electrical and Electronics Engineers, and the Society for Industrial and Applied Mathematics, a trifecta showing the breadth of his influence. In 2013, he and his LAPACK collaborators, including Jack Dongara, were awarded the ACM Special Interest Group on High-Performance Computing's Test of Time Award. The true measure of James Demmel's work is not found in the elegance of his proofs or the efficiency of his code, but in the discoveries it has enabled across the vast landscape of science. His software libraries are the invisible workhorses inside the supercomputers, tackling humanity's most pressing challenges and deepest mysteries. When climate scientists build models to predict the planet's future, simulating the dance of atmosphere, oceans, and ice sheets, they rely on solvers built on LAPACK and ScaLAPACK. The stability and accuracy of Demmel's algorithms give them confidence in long-term predictions. In engineering, the impact is equally profound. Before a single piece of metal is cut for a new airplane, its design undergoes countless hours of CFD simulations, analyzing airflow over the wings and over the fuselage. The structural integrity of a bridge or skyscraper is tested with finite element analysis to better understand the responses to wind and earthquakes, proactively managing the safety of the structures. These simulations solve enormous systems of linear equations, tasks Demmel's software is tailor-made for. His work helps make vehicles more fuel-efficient, buildings safer, and industrial processes more optimized, saving both money and lives along the way. In quantum physics, researchers probing atomic-scale materials must solve the Schrödinger equation, often a massive eigenvalue problem. Demmel's algorithms are essential for calculating electronic structure, key to designing new materials and solving inconceivable amounts of data. Beyond his direct contributions to research and software, James Demmel has cultivated a legacy through another equally important channel: education. A brilliant mind is a gift, but the generosity to share that brilliance and nurture it in others is what creates a lasting intellectual lineage. Throughout his decades at Berkeley, Demmel has been a devoted teacher and mentor to hundreds of students, many of whom have gone on to become leaders in academia and industry themselves. He's known for his clarity, his patience, and his ability to distill incredibly complex mathematical and computational concepts into understandable, digestible forms. His impact as an educator is perhaps best crystallized in his magnum opus, the textbook Applied Numerical Linear Algebra, published in 1997. This book is far more than just a collection of algorithms. It is a masterclass in the philosophy of modern computational science. In it, Demmel lays out not just the how, but the why, explaining the deep connections between the mathematical theory, the practical realities of computer architecture, and the crucial importance of stability and efficiency. The book became an instant classic, adopted by universities around the world as the standard text for graduate-level courses on the subject. It is a Bible for aspiring computational scientists. What makes the book and Demmel's teaching style so effective is its holistic approach. He trains students to think like a mathematician, an engineer, and a computer scientist. The students who pass through his classes and research group form a Demmel diaspora of talent, spreading his philosophy and techniques throughout the world. In this way, his influence multiplies, cascading down through academic and professional genealogies. In the grand narrative of scientific progress, Professor James Demmel occupies a unique and vital role. He is an invisible giant. His work is so fundamental and so deeply embedded in the fabric of modern computation that it is often unseen by those who rely on it most. Like the engineers who designed the clean water systems or the electrical grid, his contributions have become part of the essential infrastructure of our world, an infrastructure that enables discovery, powers innovation, drives our understanding of the universe. His legacy is not a single towering monument, but a strong, unshakable foundation upon which countless other monuments have been built. The principles he championed include numerical stability, backward error analysis, and communication-avoiding algorithms, which are more relevant today than they have ever been before. As we enter the era of exascale computing, where machines perform a billion calculations per second, the challenges of accuracy, data movement, and energy consumption have become paramount. The theoretical groundwork that Demmel laid decades ago now provides the critical roadmap for designing algorithms that can effectively harness the power of these new computational behemoths. His approach of co-designing algorithm software and hardware in concert has become the gold standard for high-performance computing. James Demmel changed scientific computing forever by giving the world's scientists a gift of incalculable value: the confidence to trust their numbers. Thank you so much for watching. If you enjoyed the video, please hit the like button and consider subscribing if you want to stay up to date on all things mathematical and analytical. Thanks again, and until next time, stay calculating, my friends.